A rectangular beam is cut from a cylindrical log of radius 30 cm. The strength of the beam of width W and height h is proportional to h WH squared. Find the width and the height of the beam of maximum strength. So remember again, the first step is to determine what the problem wants. Here we want to find the value of W and H that maximize our strength, so we log them to a global maximum. Here the strength S is given to be proportional, so that's gonna be K and multiply by WH squared. Now we want to write this in terms of one variable. Here I chose it to be W, so I am gonna find a way that I can write H in terms of W and plug that into the strength S. So note here, I'm gonna take this rectangle from the picture on the right. I'm gonna draw it again. Here, remember, this is a right triangle, which means this is 30 and this is W over 2, and the height gonna be H over 2. Now, what we can do, we can write this using the path theorem. So that's gonna be W over 2 squared plus H over 2 squared and equal to 30 squared. Now I'm gonna square the first term and then the second term as well as the third term. Now my goal from this equation is to solve for H, so that I can write S in terms of W. Notice here H squared gonna be 3600 minus W squared, and if we take the square root, it's gonna be positive and negative, but this is length that gonna be positive. Length is always positive, not negative. So now I'm gonna go back to the strength equation. Strength gonna be KWH squared, and now what I'm gonna do, I'm gonna substitute for the value of H squared. So H squared here again, remember, it's 3600 minus W squared. Now what I'm gonna do, I'm gonna multiply W to the what's inside the parentheses. Now we have the strength in term of W, in term of one variable. So now we can exceed to the next step with finding the maximum strength. Again, maximum strength means we want to find the global maximum. So again, this is the strength and we want to find the global maximum. So first we have to find a critical point. Is there where the function s of W equal to 0 or undefined? So now we're gonna take the function. We're just using the power rule in here. Notice here W is defined everywhere, so we don't have to worry about that. Now whereas the first derivative is 0, now what we want to do, we want to solve for W. So I'm gonna move the first term to the left side, and then what's gonna happen here, I'm gonna take the square root. Remember, the square root gonna give us positive and negative values. But remember, the W is just a length. Therefore, I'm just taking the positive value. Now this is W. It's gonna be equal to be 34.64, and the unit are in centimeters. So now I can go back and solve for h. Remember, from the top, h is equal to 3600 minus W squared. We already find W. W here should be squared, and h is the correct number in here. Now, W is a critical point, so h and W give us the critical point of the function. Now we want to see if W is a maximum for the function. So what I'm gonna do here, I can use the first derivative test or the second derivative test. Here, what I'm gonna do, I'm gonna use the second derivative test. So first, I'm gonna find the second derivative. Now, what I'm gonna do, I'm gonna evaluate our critical point, W, and the second derivative. I care about the signs in here. So note here, since we have negative, the sign is gonna be negative. Therefore, the graph of the function s concave down. So this is the shape of concaving down. We can see we will have a local maximum. Now note, since we only have one critical point of the function and it is local maximum, therefore it's gonna be global minimum, global maximum. So W again gonna be 34.64 centimeters, and it's gonna be 48.99 centimeters. These two values gonna maximize the function, the strength function.